You ever drive past something huge, like a power substation, and just wonder, how on earth did they build that? Well, it all starts with a single document. And today, we're going to take an incredible journey. We're going to see exactly how a bunch of lines on a piece of paper get turned step by step into a massive, complex facility that literally powers our lives.
This right here, this is the heart of the whole operation, the engineering drawing. Now I know, it looks like a crazy mess of lines and symbols, right? But believe me, this single document is the master plan. It has everything needed for construction. I'm talking every single detail, from the concrete foundation of the main building all the way down to the tiniest little pipe.
So the big questions are, how do you even begin to read this thing? And maybe more importantly, how does it go from being this flat, 2D plan to a real, living, breathing 3D facility? That's exactly what we're going to unpack right now.
All right, so here's how we'll tackle this. First up, we're going to decode the blueprint. Then, we'll get into the numbers, how they quantify the design. After that, we'll watch it go from a plan to a real plant. And finally, we'll check out the super cool modern version of all this, the digital twin.
Okay, Section 1, Decoding the Blueprint. So let's jump right in at the very beginning. We got to learn to speak the language of this drawing. It's kind of like identifying all the main characters before the story starts. Okay, so as we start to pull this apart, you can see the big pieces start to pop out. There's the main substation building, and over there you can see these big capacitor banks. We've got chemical tanks and their pumps, and look at this. You can trace the corridors for all the piping, you can spot the fire hydrants, and you can map out this whole hidden underground world of cable trenches and duct banks. Absolutely everything, even the roads and manholes, is laid out with total precision.
And you got to understand, this isn't just one person's job. A blueprint like this is more like a symphony, with a bunch of different engineering disciplines all having to play their part perfectly together.
And this is a great way to see how it all connects. You've got civil engineering. That's the skeleton, right? The buildings, the foundations, the trenches. Then you've got mechanical systems. Think of that as the circulatory system. It's all the pipes, pumps, and air conditioning. And finally, the electrical systems. That's the nervous system. The cables, the duct banks, all the stuff carrying the actual power. And the trick is, all of these layers have to fit together without a single hiccup.
All right, Section 2, Quantifying the Design. So, we know what everything is. The next logical step is to figure out how much of everything we need. This is where we turn pictures into real hard numbers that you can actually work with.
And there's a real method to this madness. Engineers will literally measure the footprint of every building, the distance between all the equipment. They'll calculate the exact capacity of every tank, they figure out the size, the material, and the exact path for every single pipe. And all of this information, all this data, it all flows into one super important document. And that document is called the Bill of Quantities, or just BOQ for short. Honestly, the best way to think about it is as a giant shopping list for the project. It tells the construction crew exactly what to order. We need 250 meters of this 150 millimeter UBPC pipe. We need 12 of these gate valves. We need 2 of those chemical storage tanks. It's taking the design and turning it into a real-world inventory. Okay, so that's all the stuff you can pretty much see from the outside. But what about the systems that actually make this whole place tick? Let's dive into the hidden networks, the mechanical, electrical, and plumbing systems. This is really the lifeblood of the whole substation.
So as we peel back the layers here, you can see each system light up. There's the HVAC. That's absolutely crucial for keeping all the sensitive electrical gear cool. Now see these red lines? That's the fire system, a super important safety feature. The blue lines show us the main water supply, and the green ones, that's the drainage system, which is carefully designed to make sure the site never floods. And finally, you see the mechanical skids, with all their pumps and valves. It's this incredibly complex, color-coded network, and it all has to work together perfectly.
All right, Section 3, From Plan to Plant. So, the design's all figured out, the numbers are crunched, now it's time to get our hands dirty. We're leaving the digital world behind and heading out to the real, dusty, noisy construction site.
And construction isn't random. It follows a very specific sequence. First, you dig. You've got all the excavation and trenching for pipes and foundations. Then, the pipes get laid in, but they're put on this special bedding material. That's a really critical step because it stops them from sagging or breaking down the line. After that, the big, heavy equipment is lifted into place on its foundations. Then everything gets tested and painted, and only then do they do the final step, backfilling all the trenches and making the site look good again.
But, just building the thing is only half the battle.
You have to build it exactly right. And that's where something called quality assurance and quality control, or QA/QC, comes into play. It's basically a nonstop process of checking and double-checking everything.
Here's a perfect example. Let's say the blueprint says a drainage pipe needs to have a 1% slope. Just a slight angle so the water flows out properly. Well, a QA/QC inspector will literally climb down into that trench with their tools and physically measure the angle of that pipe. If they get that wrong, water could just sit there and cause all kinds of damage. And that kind of check happens for literally thousands of details across the entire project, making sure what's built is a perfect copy of the plan.
All right, Section 4, the digital twin. Now, all this on-site checking is absolutely essential, but what if I told you there's a way to find most of these problems before a single boot ever touches the dirt? Well, welcome to the age of the digital twin.
The magic behind this is called BIM, which stands for Building Information Modeling. And I want to be really clear, this is so much more than just a pretty 3D picture. A BIM model is actually a smart digital database. Every single thing in the model, from a tiny bolt to an entire building, has a ton of information attached to it, like what it's made of and how it's supposed to work.
And the power you get from this is just immense. You can digitally stack all those layers we talked about, the civil, the mechanical, the electrical, and then run something called clash detection. That's where the computer finds problems for you, like, hey, you've got a pipe trying to run right through a steel beam here. You can simulate how the plant will operate. You can even take virtual walkthroughs of the entire site. The point is, you catch these super expensive mistakes on a computer screen long before any money is wasted building them for real.
But look, it doesn't matter if you build it the old school way or with a fancy digital twin. Once the last bolt is tightened, there is one final, absolutely critical phase before you can flip the switch: commissioning. This is the ultimate final exam, a series of tests to prove that everything works exactly the way it's supposed to.
And commissioning is this super meticulous checklist. You start by flushing out all the new pipes to get any debris out. Then you do pressure tests. You fill pipes with water to make sure there are zero leaks. You check air ducts for tightness. After that, it's time for functional tests on every single piece of gear. Does the AC system actually deliver the right amount of cold air? Do the pumps turn on and work correctly? Is there enough water pressure at the fire hydrant? This is where you prove that all the individual parts work together as one big system.
And the goal for all of this testing? It's simple, and it is absolutely non-negotiable. 100%. 100% functionality, 100% compliance with the design. Every single system has to work perfectly, no exceptions, before anyone signs off on the project.
And just like that, we've come full circle. We've seen how a flat 2D drawing gets decoded, quantified, built from the ground up, and then tested like crazy until it becomes a fully commissioned working facility. It really is a living system, operating not just in 3D, but in 4D, running day after day, year after year to power our world. It's pretty mind-blowing when you stop and think about it, right? A single drawing holds a whole universe of information, process, and hard work. It really makes you look around and wonder, what other invisible blueprints are out there, quietly shaping the world all around us?